Hello. In this video lecture, we'll be looking at a general overview of a variety of common scientific techniques. This is not at all intended to be, a comprehensive survey of all the different activities that scientists engage in order to do their work. This is just to give kind of an overall flavor of how scientists do their work. And so these are 5 different categories of kinds of scientific studies and how they're conducted. And as it says down here, there'll be some overlap between techniques. There certainly can. Every scientific research project is a little different. And so to really know exactly how they're doing their work, you kind of need to be part of it. You need to get an internship or something in order to become part of that research group and see how they actually do it. Okay. So first one, a real general thing that scientists are always doing is trying to find a difference between groups. It could be just 2 groups, or it could be multiple groups that they're trying to see if they're all really end up being actually the same thing, or if there's differences there. I've got some common examples. Biologists are sometimes looking at a large group of individual organisms, and they're trying to find out if really all those individuals belong to the same species or if they actually belong to 2 different species. And one of the things that they might do, if they're looking at birds, for example, is measure the tail length of those birds or the beak length of those birds or something like that to see if there is uh, some clear clustering, that there's one group of birds that have one certain kind of tail length and another group of birds that have a slightly different tail length, and then they can use that as part of the basis for deciding whether those are actually the same species of bird or they're different species of bird. A common one in political science would be voting preferences between citizens in different cities. Maybe there's going to be lots of diversity, right? Within any given city, there are going to be people who vote for both, let's say, Democrats and Republicans, but we might say that one city tends to be more Republican and another city tends to vote more Democrat. And they want to see, but they might be really close. And so they want to see if there's a really good difference, as we say, statistically significant difference between the voting patterns of these 2 different cities. Petal color preferences between pollinators, maybe butterflies like flowers of a certain color and bees like flowers of a slightly different color. We might try to investigate that. Different stars that are out there, see what kind of radiation, what kind of light is coming from those stars. Something much more mundane, does this laundry detergent do just as good a job as this other laundry detergent? Maybe for different kinds of stains or something, we might be trying to figure out if there's a difference between these 2. Okay. One thing worth mentioning here, although this comes up and is more important when we're doing kind of really serious statistical analyses, which we won't really cover in this video, but a common assumption when beginning here is what we call the null hypothesis. We might already assume, I mean, we're doing this investigation to see if there is a difference between these groups because we suspect that there is a difference very often. And so one starting assumption is to assume that there is no difference. And then what we're doing is we're trying to find out if this null hypothesis is true or not. Is it true that there's just no difference between these 2 groups? Or is there, in fact, a difference? So the null hypothesis would be false in that case. So, of course, what we have to do first is identify the specific property, like the tail length of the birds, or the radiation output of the stars, or the voting preferences of the people in the different cities. And there might be the case that the group that we're looking at, the giant group or the 2 different groups, 3 different groups or whatever, might all be very similar. So it might look at first as though there's not really much difference there. Or it could be that there's just so much difference. There's so much variability with, say, like the tail length of the birds. Some of them are real short, some are long, some are in between, and they're just all over the place. And that's going to become important a little bit later, but that is something to keep in mind when starting this kind of a study. Is there a lot of uniformity in the individuals that we're studying, or is there a lot of diversity and variability? Okay, so we've identified some particular property, and now we need, hopefully, as consistent and reliable a way as possible of measuring that particular property. If it's something straightforward like tail length, well, then we need just a good measuring device, like a good ruler. And what exactly is the starting point of the tail, and what exactly is the end point of the tail, so that we can get a good consistent way of measuring tail length for all the different individuals that we do this for. So that's pretty straightforward. But there might be much more difficult things like behavior patterns. Say that we're looking at groups of primates and we're trying to figure out if there's a difference in the level of cooperation or aggressiveness amongst these primates. Well, how cooperative are they? We don't have a measuring device for that. It's, as we call it, a qualitative measurement, as opposed to a quantitative measurement. A quantitative measurement is one where we have a specific measuring device that and specific units that we're using, and it gives us a final number, a quantity. So tail length in centimeters, for example. But for aggressiveness or cooperation or these kinds of things, it's a little bit of a judgment call. So the researchers ahead of time would have to come up with, as best they can, a very consistent and reliable way of judging whether a certain kind of behavior on the part of the primates counts as aggression or cooperation or neutral, just nothing. So preferably we want it to be quantitative, but it's not always possible to have that. Then we measure all the individuals in each group, or as many as we can, calculate the average for the groups, and then see if the average comes out to be the same or different. So what we could do, if there's a relatively small number of individuals in the groups that we're looking at, is measure every single member of all the groups. It could be just two groups or many groups, as I said. So measure all of them and then take the average, and then you've got a final answer, a definitive answer as to whether there really is a difference between these groups or not. But in normal circumstances, under real conditions, that's rarely possible. Usually we're dealing with thousands or maybe even millions of individuals. So it's practically impossible, really, to measure every single individual. So instead, we take a representative sample from each group as best we can, take a representative sample of individuals from each group, and then measure the relevant property in those individuals in the representative sample, take an average of those individuals and compare them. And then hopefully our representative sample really does represent the larger group. So if we find a difference between the representative samples, then we know that there's a difference between the groups themselves. So how do we do that? Well, there's lots of different techniques. It depends on the particular circumstances, but something we might do for birds, for example, is just collect a random sampling of the birds from each group. We try as best we can not to favor a particular location or anything like that. We just get as much as we can a random sampling of all the individuals in the groups that we're interested in. Now, sometimes random sampling like that could end up just accidentally getting a non-representative sample. For example, with the birds, again, it could be that almost all the individuals you gather just happen to all be males or happen to all be older birds or all younger birds or something. So you might want to do some intentional balancing of your representative sample. So it's not just purely random selection, but you try to get a good representation in your sample for the range of ages and sexes and so on that are in the real group that you're interested in. Sometimes you might need, in fact, usually you will need a very large sample in order to make sure that you're getting a good representation of the overall group. If you pick just a few individuals, it could be, without you realizing it, that you picked some quirky individuals that have somewhat unusual characteristics relative to the whole group. So you want to get a good large size. Okay, so then once you've got your representative sample and you've done your measurements, then you calculate the average for each of your samples and compare them. Now, the comparison process is where this diversity issue comes into play again. Um, if the individuals in the groups that you're measuring uh, are all very similar to each other within each group, but not similar across groups, then it's a little easier. But if there's a huge amount of diversity in both groups, it can be hard to tell. Even if you get a difference in the averages for the representative samples that you've collected for each group, it could be that you got kind of a false sense of exactly how much difference is there. If there's a huge amount of diversity in the groups, then you might have just happened to pick individuals that have, say like longer tail lengths from group A and somewhat shorter tail lengths from group B without you realizing that that's what you did. So you might have to, and this is where some fancy statistical analysis can come back into the picture, is calculate the standard deviation, as they call it, from the average. So here's a real simplified sense of what that would look like. So in the top graph here, let's say again, this is tail length for birds. And so on the x-axis here, we've got length of the tail, perhaps in centimeters. And then on the y-axis, we would have the number of birds that have a tail with that length. So here we've got two groups, Group A and Group B, represented by these two bell curves. And as we can see, the average here is different, right? We've got a difference between these groups, but there's such a large diversity, right? Such a huge spread of tail lengths represented in both groups, and a whole lot of overlap between the groups that, yes, we found a difference in the average between our representative samples, but we have a somewhat low confidence that this shows us that there really is a difference in the averages between the two groups overall. It could be just a quirk of what individuals we selected for our representative samples that gave us this result. Now look at the bottom graph. So here there's almost no overlap between the groups at all, and significantly less spread of diversity within each group. So here, now we've got the same average, right? You can maybe see that these peaks are in the same spot. So this is supposed to show that we saw the same amount of difference between these groups in the lower graph as we did in the upper graph. But since there's such a tighter bell curve, so there's not as much diversity within each group, and there's very little overlap between the groups, we can have somewhat higher confidence that this difference that we found in our representative samples really does show us that there's a difference between the groups overall. Okay, but to really know that for sure, you do have to run the actual statistical analysis, run through the equations. So here, these next couple slides are just sort of showing in print what I was just explaining. So a few other things to take note of when we're trying to find a difference between groups. And this really depends on what sort of thing we're actually measuring, what it is, what kind of a difference, what the property is that we're measuring to see if there's a difference with respect to that property. So blind testing of some kind. So the subjects being tested don't know what group they're in. Now, if we're talking animals, it's irrelevant. They don't think in those terms, of course. The birds don't know what group we think that they belong to. But if we're dealing with human subjects, so especially if we're dealing with some new medication that's being tested, we're trying to find out if that medication works or not. We know that just knowledge that you've received the medication can have a strong effect on your physiology and your outcomes, how much better you get or how much changes happen in your body. They call that the placebo effect, of course. So as much as possible, we would want those human subjects not to know what group they belong to. So that they don't, their knowledge of what group they belong to doesn't affect the outcome. The subjects don't know what they're tasting, hearing, or touching. This could be if we're doing a taste test between, say, like different sodas, right? Different colas, Coca-Cola versus Pepsi, the taste challenge like that. Which one do people prefer? Well, you shouldn't let them know ahead of time whether they're about to taste Coca-Cola or they're about to taste Pepsi, so that they aren't affected by that knowledge. They might already believe themselves to prefer one over the other. So if they know which one they're tasting, that can bias their responses. Then this third one is the most common one that shows up in lots of different studies of this kind, that the people doing the measurement don't know which group they're measuring. So again, if we go back to medications, the people that are evaluating the outcomes for these patients, they don't know if they're looking at a patient that did receive the medication or did not receive the medication, so that they can be fair and unbiased when doing their evaluation. Ideally, though this is hard to have it work out for practical reasons, but if we go back to the bird tail length example, the person that's doing the measurement of the tail length, maybe they aren't told which group this particular bird they're looking at, which group it comes from, because they might already have in their mind that, oh, the birds from this group tend to have longer tails. And it's possible, though they're using like a quantitative measuring device, but it's possible that it might infect the way that they do that measurement. More likely is the primate example. If there's somebody that already thinks that one group of primates tends to be more aggressive than another group of primates, when they're doing their observations of the behavior of those primates, their previous conceptions, their assumptions can bias the way that they do their evaluation. So if they see some particular behavior, they might be more likely to interpret it as aggressive behavior if it's from a member of the group that they already believe to be more aggressive. So ideally, you would want whoever's doing the evaluation of whether this is aggressive behavior or not, you would want them to not know which group this primate comes from, so that they can do a fair evaluation. Okay, moving on to the second technique. And this actually is very similar. And I even gave with some of my examples, ones that more properly belong in the second category, but this is very similar to the first category, because we're going to be finding a difference between groups again. But what we're going to do here is, rather than just seeing if there is a difference between groups, we're specifically going to see if there's a difference between groups with respect to some particular thing we did to those groups, right? We introduced something to the groups, or we removed something from those groups, and we want to see what effect, if any, that has on the groups. So in order to do that, we first need to identify and control as many different variables as we possibly can, because we want the final result, a difference between the groups or no difference between the groups, to be a result of only a result of the variable that we are interested in. We want to make sure that none of the other variables that are playing a role have an effect on the result. So we want to identify and control as many different variables as we can, and I listed a bunch of them here. Of course, this is best done in a controlled laboratory, where you can control all, the temperature and the lighting, the time of day that this is happening, and everything possible. Much more difficult if you're doing it, in a human society, or doing it out in an ecosystem or something. One group, at least one group, you take representative samples, again, from the population that you're studying, and one of those representative samples, you designate the control group, and you have that set at some kind of standard baseline. All the same temperature, all the same time of day, that sort of thing. And then you have at least one other group where you pick one variable that you're changing. So maybe you are modifying it from baseline, or you're introducing something brand new, or you're removing something that would have already been there. And then you're going to try to see if that has an effect. Again, we start with the null hypothesis. And again, this is particularly important for when we're doing a real statistical analysis. But the null hypothesis assumes that there's just going to be no effect. Whether we introduced something new, or removed something, or we just changed a variable, that it's going to have no effect. And the groups are going to be this as if they were all just the control groups. And then once we've done that, as it says at the bottom here, we compare the groups just like we did in technique number one. I do have a video on the differences between experimental and historical science, because historical science, you can't control variables in this way, because you're looking at things that have already happened in the distant past, perhaps distant past, maybe even in the more recent past. So go ahead and check out that video for more details on this, but I'll just kind of bounce through these. Okay, so this third technique isn't really an experimental technique, but it is a common thing that scientists do. And often it's a kind of a precursor to a more detailed study that might involve actual experimentation, like in example 2, where we're trying to find the cause of or the effect of a specific cause that we either introduce or remove. So here we're just kind of like seeing what happens, right? We get this very large sample, say like all the different birds or all the different people in a country or something, measure all sorts of different variables, whatever we think might be relevant, and then just look for trends. So correlations between variables. Do people in certain locations in the country tend to have certain voting patterns versus people in other parts of the country? Or people of certain ethnicity tend to have certain diseases or disorders more than people of a different ethnicity. Or certain diseases or cancers show up in one place versus another place. We don't really know necessarily ahead of time. We might have some reasons why we're starting to do this study in the first place. So we might focus on certain properties of the individuals and the groups that we're looking at. But nevertheless, we're just kind of like seeing what's out there. Now, once we find a correlation between variables, we always have to remember, right, that correlation does not automatically indicate causation. So we might think that a difference in disease rates between groups, people living in one part of the country versus people living in another part of the country, we might have some guesses as to what's causing that difference, but we would need to go back to technique number 2 to really be sure, right, where we're trying to find a specific cause for a particular effect. Number 4 here is very similar to the last one, but this tends to be a little more focused. So we might be just sort of cataloging specific things. When we go back to astronomy, especially into the ancient past, really, we could think of that as one of the first real sciences was astronomy. And because they were systematically cataloging all the different astronomical objects, where they are relative to each other, which ones move relative to each other, which ones don't, how do they move over time, do the patterns repeat, do the patterns not repeat, all of that kind of thing, just keeping records. Setting up almanacs, for example, that catalog all of this data so that scientists have this information that they can refer back to if they want to conduct a more focused study on some particular group of items, or they want to maybe do one of these finding a difference between groups or finding a cause for a particular effect or any of those other techniques that we talked about earlier. They'll have this data as kind of a baseline for them to sort of get themselves oriented. The 5th one then is modeling. And this is when we want to study some system, some natural system or some human system that is just far too complex or difficult for us to be able to study it directly, or we can't manipulate it directly. We can't set up control groups and experimental groups. So a really common example around today is climate. So the Earth's climate. Extremely complex. And we can't manipulate it. We can't introduce new variables intentionally in some controlled way to see what effect that introduction of that new variable has. Partly that's unethical, partly it's just too big and difficult, and it's sort of a chaotic system. So, and it takes too long for the results to come in. And so instead of running tests on the climate directly, we consult or we construct a model of the climate. We take the variables that we think are important, so temperature, wind speed, reflectivity of water versus land versus ice versus clouds and so on, different kinds of clouds, humidity, all of these different things. We take all these variables and we plug it into an equation, in this case, computer modeling is the most common kind of modeling, and then we run the equation to see what comes out. So hopefully the behavior of our model, when we change its variables, gives us good insight into the thing in nature, the system in nature that we're actually interested in. So, of course, the concern is that we've created a model that is just not similar enough. And so we've got this difficult balance between having a model that's simple enough for us to be able to understand it and manipulate it and use it. But the more simple it is, the less similar it is to the real version. And so it might be like an interesting model, but it doesn't give us any real insight into the way things actually happen in the real world. But then if we add in more complexity to make it more similar to the real world, then it becomes more difficult for us to understand and manipulate and use our model. So as I mentioned, computer modeling is by far the most common here. And with the rise of computer power, these kinds of models, especially complex climate modeling, has gotten better and better and better and more accurate. So in order to be sure or get some confidence that our model is an accurate reflection of nature, we have to regularly compare the results of our model to what we actually observe in the complex system in nature that we're really interested in. So for example, we have some pretty good knowledge of how the Earth's climate has changed over the last, let's say, 10,000 years. And we might also have some good knowledge of what the Earth was like 10,000 years ago in terms of its temperature and rainfall, humidity, cloud cover, and all of those kinds of things. So we plug those variables from 10,000 years ago into our computer model now, let our computer model run for the equivalent in computer time of 10,000 years, run it forward to 10,000 years and see if the results of the model are the same as the results that we actually observe now. If so, then we can have some pretty good confidence that our model is matching the real actual system in nature. Or we might make some predictions using our model for what's going to happen with our climate in 5 years. And then as 5 actual years go by, we see if our prediction actually matches what really happened. And again, that can give us more confidence. If it's a good match, it can give us good confidence that we've got a useful model. Okay, so some things to watch out for, especially when we're talking about the causes for certain effects, is these two things, false positives and false negatives. So a false positive is when we get a specific result, we get an effect. Maybe it's the expected or the desired result, maybe not, but we get an effect and we observe it, we measure it, but it turns out that for some reason, it's not really what we thought it was. That perhaps our representative samples that we were using, there's just too much diversity within them, as we talked about before. So even though we saw there was a difference here in the averages for the property that we measured between these two groups, but it turns out that it was something quirky about the individuals that we selected for our representative samples. So there's not actually a difference between the groups, sort of in the larger groups out there in the real world. Or it could be that the effect that we observed was a real effect. There really was this difference between groups, but it was the result of a cause that's different than the cause that we were actually looking at, that we were manipulating and expecting. And so if you do this, if you report to the world, you say, look, I found this effect on this positive result. Say it's a medication that you're developing, and you say, look, this improves the outcomes for patients that take this medication, but then it turns out it was a false positive, then people might stop believing you. And that can really damage your scientific credibility. And if your scientific credibility is damaged, then funding agencies are much less likely to give you funding for doing more research, and your career could be over. So this is extremely important for scientists to watch out about reporting false positives. They do everything they can to make sure that their results are reliable and that they can defend these results to the larger scientific community. False negatives are also important, perhaps not as damaging to a scientific career. if somebody reports a false negative. So this is when the result is not found. Say the null hypothesis is upheld, right? That there is no difference observed between the groups. And this could be that you just didn't look closely enough. Perhaps the individuals that you selected for your representative samples were just too similar to each other, so they weren't really representative of the larger groups that you got them from. So there really is a difference between these groups, but there's just not much of a difference between the representative samples that you collected. Or you're just somehow there's just a mistake in the way that you measured it. And so this is important because you might give up. You might say, oh yeah, this isn't working. We didn't find anything. There's no reason to follow up on this. If it's a medication, again, I think is a good example here. You said, oh, looks like this medication just isn't working, so you abandon it. But it could be that there was something very promising about that you missed. Some examples of false positives. One that's come up a number of times in history is this cold fusion. This is a new way of generating electricity with negligible pollution, negligible sort of negative like waste products. Very, very difficult to achieve. So there have been research groups in the past that have said, yes, we're there, we've done it, we've got this positive result, we're on our way to this energy revolution. But then it turns out that nobody else could replicate the results. And then when that group was asked to show everybody, they couldn't even replicate their own results. And so they just jumped the gun, right? They weren't careful enough in checking everything that needed to be checked in order to be confident and convince the larger scientific community that this positive result was a real result. And that very negatively damaged their scientific credibility. N-rays is sort of a quirky historical example that I like. This was soon after X-rays were discovered for interesting reasons. X-rays are invisible to our eyes, so we need special devices, special techniques for detecting X-rays. And once they were detected, scientists were really kind of blown away. They're like, wow, this is kind of electromagnetic radiation that we can't see. It's out there, but we can't see it, and it might be very interesting. And then soon after, there was somebody that claimed they had found something similar. They called them N-rays. But it turned out that really there were a bunch of problems with the way that they were studying this. Nobody else seemed to be able to detect these N-rays, and so it was a false positive. And I already described some examples with medical testing that you say some new medication. It's, oh, wow, it's really working. It's doing a great job. It's really having a positive effect on these patients. But then it turns out over the long term and more people are given this medication, it starts to become clear that it actually doesn't really work. And it might even have some bad side effects. So again, we have to be very careful about reporting a positive result of some scientific study before we're sure we have done the necessary work to have very high confidence that this result is reliable. False negatives, criminal investigations, I think, is a good example where some suspect is ruled out. We say, oh yeah, looks like they didn't do it, but it turns out we hadn't seen all the relevant evidence, and so they actually did do it. So we let a guilty person go free. And the medical tests again. You say, oh, it looks like this medication isn't working, and so you stop pursuing it, but it could be that that medication actually does work quite well. It's got some real promise if you had just stuck with it. All right. The long-term goal of all of these kinds of scientific studies is understanding nature. What is out there? So those surveys and cataloging, what's there? And then how does it work? Why does it work the way that it works? How do we change how it works? Can we manipulate it in some way to gain a deeper understanding and to answer these how and why questions? These are the kinds of things that scientists are trying to do, ultimately, over the long term. Produce that kind of answer, that kind of understanding that can answer these how questions and these why questions. All right, thanks. We will go ahead and stop there.